We are talking about limits of functions, and I said at the end last time a sequential criterion for limits. Sequential criterion. For limits of functions. I will just write again what I said at the end last time. Lim x goes to c f of x equals L is equivalent to, so the one on the left is the thing that you're using several times on the homework. You do this, the epsilon and delta. The one on the right is an equivalent condition in terms of sequences, and it says for all sequences, let's say xn, which approaches c, we have f of xn is another sequence, and it approaches L. So this is another way to formally say something like, as the x's approach the c, that's this thing, as the x's are approaching c, which means if you have any sequence of points approaching the c, then the same sequence, when you plug it into f of x, the sequence of y values approaches L, the limit over here. All right? Now, this is actually, so the thing on the right side is not very convenient to use to prove that a limit actually exists, because you need to somehow consider all possible sequences and then prove that this other sequence goes to L. And this is difficult to do directly. So you don't actually use that thing over there to demonstrate that a limit equals something or other. But it actually leads to some sort of theorems for free, this point of view, and also it's very useful, I think I mentioned last time, it's very useful to use the other side when you're trying to demonstrate a limit does not exist. But let's just talk briefly about sort of theorems for free. Because of this, so I will just say we can rephrase continuity of a function, not continuity, sorry, limits of a function. We are going to talk about continuity, but I don't know if we'll get there today. We can rephrase limits of functions as limbs of sequences. And in particular, this gets us some sort of free theorems. I'm thinking of the theorems about adding two sequences together, like if an approaches a and bn approaches b, then an plus bn approaches a plus b. Those are, like, we call them the algebraic limit rules for sequences. Because those things are true of sequences, they are automatically true of functions. So we don't really have to go through proofs of that again for functions, because we know that the limit of a function is equivalent to the limit of some other sequences. And using the fact that those rules hold for sequences, it means they automatically hold for functions. So I'm going to say something like, for free, we get this. I'm going to write this as like a big theorem here. For free, I mean, if you wanted to write out the proof of this, all it amounts to is, first of all, shifting from talking about functions to sequences. And then we already know these theorems are true for sequences. So I'm going to say if f and, I'll say it this way. If lim x goes to c, f of x equals L, and lim, I have another function, g. So if the limit of f of x is L and the limit of g of x is m, then we can add them up and you get L plus m. That's what I'm going to say here. So although that actually, this is going to have a few parts to it. I'll say also, and k is a real number. Then, all right, number one is just about constants. If I have the limit of k f of x, this equals k times the limit of f of x, right? Which, if you like, you can write it as KL, because I said up there that limit of f of x is L. All right. Why is this theorem true? It's because we already know this is true of sequences, and you can change this limit of a function into some limit of a sequence, and then use the rule for factoring a constant out of a limit of a sequence, and then change it back into functions afterwards. All right. There's also, so number 2 is the rule about adding together. So lim x goes to c f of x plus g of x, like this, is equal to, it's the limit of the first one plus the limit of the second one. Lim of f of x plus lim of g of x, which, if you like, you can write as L plus M. All right. These properties, to a calculus student, these are all sort of obvious properties. You use them all the time without even thinking about them. All right, and then I got 2 more. One is about multiplication and one about quotients. You might worry about, don't I got to do like the product rule or something with the multiplication? No, you don't. With an ordinary lim, there is no special product rule. If you're doing a derivative, then yes, there's a special product rule. But with an ordinary limit, when you have 2 things multiplied together, you can just multiply the 2 limits together. Exactly the same rule for sequences. Like so. So it's L times M. And then finally is the quotients one. F of x divided by g of x. And the answer is lim of f of x divided by lim of g of x, which I could write as L over M. And this one, a little technicality, this is true when M is not 0. If M is 0, there's no telling actually what it could be. If M is 0 and L is not 0, then the limit does not exist. But if they're both 0, you could get some weird business happen. All right. So these are the algebraic rules for limits. They add up, they multiply. These are super useful properties you use all the time, like I said, without even really thinking about it. And we don't really need to do proofs of this because the way you would do it is translate these facts, these statements, into statements about sequences, and then we have already proved those statements about sequences. All right. Any thoughts about this? We actually don't have much to say about this other than these are real rules and you can use these rules, and we will use them, although there's not much to say about it. Great. Let's talk about the other useful thing that I said about this this business here, right? This is super useful in showing that certain limits do not exist. For example, how to show limits do not exist. Question mark. How to show limits do not exist. For example, here is an example of a limit which does not exist. Lim as x goes to 3 of 1 over x minus 3. This does not exist. Everybody knows that. How would you demonstrate that? Actually, using the definition of limit with the epsilon and the delta, this is actually quite difficult to do. It's just a real pain to demonstrate. So this does not exist. What that means really is, i.e., there is no L with lim x goes to 3, 1 over x minus 3 equals L, right? That's what I mean when I say the limit does not exist. There is no number which equals that, all right? But to demonstrate that involves negating the definition of a limit. So you take that for all epsilon, there exists delta such that whatever, and you do the negation of that. It turns into there exists epsilon such that for all delta, and then some other weird stuff with the rest of it. This is, I'm just going to say, this is hard to demonstrate. Using the epsilon and delta definition. But with sequences, not so bad. not so bad with sequences. All right, I will refresh our memory of, the thing that I said at the very beginning. For example, if we say this, lim x goes to 3, 1 over x minus 3 equals L. This is true if and only if, for all sequences xn approaching 3, we have f of xn, sorry, I don't want to use f. I will just write, what is the function in this example? It's 1 over, so it's this, 1 over xn minus 3 equals L, right? Now, can I prove the opposite? Actually, that thing over there on the right side is not so hard to write what its negation is. It doesn't have that like double quantifier thing in it. It's just, sorry, I didn't mean equal, I mean approach. This is a sequence which approaches L. Sorry about that. It is, if you take sequence in the domain approaching this number down here and plug those numbers into the function, that sequence of points approaches L. All right? The thing is, this over here is not so hard to negate. Right? The opposite, so it just says for all sequences that approach 3, that other thing approaches L. The opposite of that would be there exists some sequence which approaches 3, and the other thing does not approach L. That's the negation of that. So the opposite would mean, I would say lim x goes to 3, 1 over x minus 3 does not equal L. This means, I'm writing the opposite now. It means there exists a sequence xn approaching 3 such that 1 over xn minus 3 does not approach L. And this is actually fairly easy to demonstrate. All you have to do is tell me a sequence which approaches 3, but when you plug that sequence into the function, it does not approach some number L. All right? This is not so hard to do. Can we just try this out here for this one? I would like to think of a sequence. We need a sequence xn which approaches 3, but 1 over xn minus 3 does not approach anything, right? Really, I'm trying to show that there is no limit at all. We don't even know what the L is, but this, can I say, does not approach any limit L. Any ideas? All it takes is you just have to think of an example, all right? Which is a lot easier than trying to write some kind of complicated proof. My example is always like 1 over n, right? Although that approaches 0. Anyone want to suggest a modification, perhaps? 1 over n plus 3 is the correct answer. This is exactly what I would have thought of doing. I would have also accepted 3 minus 1 over n, if you want to come the other way, or 3 plus 1 over n, come the other way, right? But this is a good idea. So let's try xn equals, did you say plus?
Yeah.
3 plus 1 over n. All right? This does approach 3. And what about 1 over xn minus 3? Well, I can just plug in my formula for xn. It was 3 plus 1 over n. Am I blocking the view? No? All right. I don't want to. Okay, plug it in. It's 1 over, xn is 3 plus 1 over n. So down here it's 3 plus 1 over n minus 3, right? I plugged in my formula for xn. Xn is 3 plus 1 over n. What happens there? My goal is to demonstrate that this does not approach any limit. Is that really true? I think I can cancel the 3's, and I get 1 over n, which is n. This is like my other favorite sequence. N. Does n, just the sequence n, have a limit? No, it does not. It is unbounded. So I would just sort of, if I'm trying to be very explicit in my conclusions, this is actually the same as the sequence n, right? Which does not approach any limit. All right, so that means that my conclusion is lim x goes to 3, 1 over x minus 3 does not exist. There is no limit. All right. So when you ever want to show that a limit of a function does not exist, it suffices to just invent an example sequence which acts in that way, where the sequence does approach sort of this little number down here, but when you plug it into the function, it does not approach anything. It's unbounded, or maybe it oscillates or something like that. All right? So let me just write, I'm going to try and write this as explicitly as I can, just so that you have it in your notes. I'm going to write it as a theorem. It says lim x goes to c f of x does not exist. This is the easiest way to show that a limit does not exist. If and only if there exists a sequence xn which approaches c with the sequence f of xn divergent. All right. This is the go-to way to show that a limit of a function doesn't exist. You make up a sequence so that when you plug the sequence into the function, it diverges. All right. Now that example that we did up there was divergent because this is unbounded, like that sequence goes up to infinity. Although there are other ways the sequence can diverge. Divergence means it doesn't converge, so it's possible your sequence could maybe oscillate between two values or something like that. Here's an example of that. Let's try. This is a slightly fancier example. How about lim? This is one of my favorite functions. This is a classic, like, topologists like this function a lot. Sine of 1 over x. I don't know if you've ever seen the graph of this. You want? Let's. Would you mind if we? I'm gonna pop over to my graphing calculator just to show. So I said sine of 1 over x. I don't know if everyone is familiar with this function. It looks like that. If you think about just 1 over x, it increases like crazy near the origin. And when you plug those values into the sine, the effect of that is the oscillations of the sine of x just oscillates increasingly rapidly as you approach the origin. And you get this weird thing like that. It looks like a solid bar, but really what it is the curve is just oscillating sort of infinitely rapidly as you approach the origin. And what is the actual value when x equals 0? The answer is there is no value when x equals 0, just because that's in the denominator. So this function is undefined when x equals 0. And this is a good example of a function where you can't even, like, some functions are undefined at a particular point, but you can sort of like plug in the value of that point to make it continuous, but that's not possible here because this function kind of approaches all values in that strip as you get close to the origin. Anyway, this is what I'm trying to demonstrate. This does not exist. The limit as x goes to 0. Let's try and prove that. Proof, I guess. It's just really an example you have to provide. We have to think of a sequence approaching 0 where the when I plug it into the function, the limit ends up not existing. Anyone have an idea? What's your favorite sequence that approaches 0? You all know the answer is 1 over n. Actually, 1 over n is not a great example to use here because let's just see what happens if I use 1 over n. Then I'm going to kind of scribble this out, so you might not want to write it down, but Then I plug that into the function, so I go sine of xn. This would be sine of 1 over n, right? I'm plugging in 1 over n where x is. Of course, that is sine of n. And then what is this sequence? Does that converge or diverge? The answer is it diverges, although this is a little difficult to say for sure that diverges. I mean, this is a very strange sequence. It's like sine of 1, which is just some random weird number. Sine of 2 is another weird number. This sequence is not all that convenient to talk about. Anybody got so you can sort of do some tricks maybe. Change this around a little bit so that what you get here is actually a nice sequence. Any ideas? The fact is, I don't like plugging a whole number into sine, right? Because you get some weird nonsense. Think about, like, what do you like to plug into sine? And then make your sequence to have that kind of stuff. Be the change you want to see.
It'd be like 1 over pi n.
Yeah, something like, yeah, put pi in here somehow so that when you end up plugging it in, you get something that works nicely. I think actually, he said 1 over pi n.
Yeah.
This is a good idea, although it for technical reasons doesn't work out great. Let's see what happens. If I go 1 over pi n, then I go sine of xn is sine of 1 over pi n, which is sine of pi n. So this is sine of pi, sine of 2 pi, sine of 3 pi. What can you say about those values? Remember your sines and cosines? I believe those are all 0, right? Sine of pi, sine of 2 pi. Actually, this was this is a great idea, although it ends up being kind of a bad result here, because actually this one does converge. It's 0 every time. We wanted to choose a sequence which does not converge. Any other ideas?
Pi over n?
Pi over n.
And then it would be sine of n over pi.
Yeah. Is that good? You get like 2 over pi, 3 over pi. Those are not things that I like to take the sign of. I like pi over 2, pi over 3 I can handle, but 2 over pi I don't like. How about
So n over pi. You do 2 over pi?
I like 2 over pi n better. If I put 2 over pi n, I'm going to end up with sine of pi over 2 times n. I like that a lot, actually, because sine of pi over 2, and then sine of pi, then sine of 3 pi over 2. So all of these are good ideas, helpful steps along the road, although not what we want exactly. I'm going to say let xn equal 1 over, can I write it this way? 1 over pi over 2n. She said 2 over pi n, which is the same thing, but this is, to me, this seems a little bit clearer. And so the sine of xn is the sine of 1 over pi over 2n, which is the sine of pi over 2n. And this, I like this sequence. What are the values of that sequence? Sine of pi over 2 is 1. Sine of, the next one would be pi over 2 times 2, which is pi. That's 0. This sequence actually is 1, 0, minus 1, 0, 1, 0, minus 1, 0, etc. That's what that looks like. Yeah?
So where we write sine of xn, should we use sine of 1 over xn? Because I'm just a little confused on how we get...
Yeah, thank you for that. I did it wrong 3 times. Yes, it's always sine of 1 over xn. Thanks. Because this is the function, sine of 1 over x. Yeah, sorry about that. Anyway, the sequence we end up with is this. And does that sequence converge or diverge? The answer is diverge. How would you say specifically, how do you know this diverges?
subsequences that go to different
Right,
ones.
because you can find two subsequences which converge to different values. All right, so this diverges since we have a subsequence converging to 0, for instance. If you take the, I guess the even number terms, it converges to 0, and another one converging to 1 if I take every fourth term. All right, and if you have two subsequences converging to different values, that means the original sequence diverges. That was some old sequence stuff that we used to talk about. All right. So sometimes you have to, there's a little bit of a journey to come up with your perfect sequence which makes everything work out the way that you want. All right. Here's another very slightly related, I mean, this is very similar, but another theorem that you can use to show that a limit does not exist. Actually, this is one I think I wrote it slightly wrong on my paper. That's all right. Lim x goes to c, f of x does not exist. If there exists two sequences, xn approaching c and yn approaching c, with lim f of xn not equal to lim f of yn. So this is a very slight variation, but this sort of lets you kind of jump directly to this business about two subsequences going to different values. If you can think of two different sequences so that when you plug them into the function, they go to different, they converge to different values, then automatically the limit of the function cannot exist. All right. Sometimes this is a little easier to do than the other strategy. Yeah.
In that scenario, do they both have to be convergent, or could you have one that's divergent and one convergent somewhere else?
No, if one diverges, actually, if one of these diverges, then you don't even need the other one, because we already said, like this here. If you have one sequence which diverges, then already the limit does not exist. So this is, if you can do that, then that's even better. But sometimes this is a little easier to manage. You can think of two different sequences where they each converge, but they converge to different values. All right. So, and I got an example of that also, and then we'll talk about continuous functions. How about this example? How about the limit as x approaches 1 of, remember this thing? This was in one of our homework problems. This is the greatest integer function. It's the, also known as the floor. It's the greatest integer less than x. You can think of this as just rounding down the number. So for instance, the greatest integer of 4 is 4, but the greatest integer of 3.7 is 3, right? You just throw away the decimal part. The greatest integer of pi is also 3. All right, the graph of this, if you like, looks something like, anyone know what the graph of that looks like? Yeah.
Just be like a bunch of lines that are staggered on the integers.
Yes, it's like, this is sometimes called a step function. It looks like you got one of these, and one of these, one of these, where these are the integers. It goes like that. And they have, there's sort of like this sort of a dots situation, filled in and an empty dot. Which one side is filled in, one side is empty? Which one is it going to be? Yeah?
The left side is.
You got two choices.
Oh, the left side is filled in with the right side.
That's right. The left side is filled in. and the right side is empty. If you think about, for instance, 4, the greatest integer of 4 goes up to 4. That's 1, 2, 3, 4. So this one has to go here, which means that side should be filled in, and that means automatically the other side of the next lower one has to be empty.
Okay, so
Yeah.
is the greatest integer less than or equal to?
Less than or equal to,
Okay.
yes. So I should have wrote that. You know, I have this problem with less than's versus less than or equal to's. Sorry. Less than or equal. Thanks. Okay, so it looks like this. All right, great. Etc. And it kind of goes on forever like that. All right, I would like to say, what about lim as x approaches 1 of this function? 1 is right here. Does the limit exist as x approaches 1? I see some shaking of the heads. Yeah, it does not exist. This is one of those times when, like, the limit coming from the left does exist, the limit coming from the right does exist, but they are two different things. And so we say the overall limit does not exist. Can we try to demonstrate that using the sequences or whatever? Lim x goes to 1 of the greatest integer of x does not exist. All right. How are you going to prove that? Well, your options are you either find a sequence so that when you plug it into the function, that sequence diverges, like that sequence has no limit, or you could find two sequences approaching 1 so that when you plug the values in, you get two different answers. And actually, in this example, the second strategy will work better. Can you think, it might help to look at the picture here, can you think of two ways that you could approach 1 so that when you plug those values into the function, you get a different answer either way? Yeah?
Did you do 1 plus 1 over n and 1 minus 1 over n?
Mm-hmm. Yeah. I think she's thinking about the fact that if you approach 1 from this side, then the values of the function are always 0. But if you approach from this side, the values of the function are always 1. So my two sequences I'm going to use are one which approaches from the left side and another which approaches from the right side. And then they should end up having two different limits. And what's your favorite sequence approaching 1 from the left side or the right side? It is 1 minus 1 over n or 1 plus 1 over n. Those are your two choices, really. Or I suppose you could do something like 1 plus pi over 2 times 1 over n or something. That you should only do that if you really want to, like if there's a reason to. Otherwise, just use 1 over n every time. So I'm going to use xn equals 1 plus 1 over n and yn equals 1 minus 1 over n. And I want to show that the lim of f of xn is different from the lim of f of yn, right? That's the idea. These limits, I expect one of them will be 0. The one on the left, the limit should be 0, but the one on the right, the limit should be 1. That's what I expect to happen. So I'm going to say, what about f of xn? This would be the greatest integer of 1 plus 1 over n. What are those values? I'm talking about something like 1 over 2. No, 1 plus 1 over 2, or 1 plus 1 over 3. What is the value of this? You just round down. It throws away the decimal part, or throws away the fraction part. You just end up with 1, right? Now, I think, technically speaking, the first term of this sequence is a 2, but then all the rest are 1s. Because when you use n equals 1 there, you actually get 2, which does not round down to 1. But all the other ones, you get 1 plus a little bit, which rounds down to 1. Right? And what about the other? F of yns. This is the greatest integer of 1 minus 1 over n. What does that sequence look like? Yeah.
1, 0, 0, 0, 0.
Yeah, all zeros. Although you should wonder about the first number. Is the first number a 1 or a... I think the first number is also a 0 here. When you use n equals 1, it looks like 1 minus 1, which is 0. Yeah, it's weird that the first one there has a different starting value and the second one doesn't. It's just how it goes sometimes. All right. Anyway, I hope you agree. Lim of f of xn is 1. Lim of f of yn is 0. And these are not the same, which means the function does not have a limit. All right? Not the same. So lim x goes to 1 of greatest integer of x does not exist. All right, you got to think up some clever sequences. Any questions about that? I have a little warning here. All right, so to show limits do not exist, use sequences. All right. Almost always, this is the way you should do it. All right, this is sort of the moral of the story for today. To show that certain limits of functions do not exist, you use sequences. You invent a sequence for which the sequence diverges when you plug it in, or maybe two sequences where you get two different answers. But to show limits exist, you must use the epsilon delta thing. All right, I will say demonstrating a sequence is not enough. To show that a limit actually exists. Yeah?
So is that just like a class thing, or like in general mathematically?
No, this is a true fact. In order to show that a limit does not exist, it's enough to just demonstrate a sequence where that sequence diverges. That means automatically the function cannot have a limit. But if you demonstrate a sequence where the sequence converges, does not demonstrate that the function also converges. Because your sequence is really just picking out like individual points.
Oh, really?
That's not enough to show that the whole function converges. So, like, for example, if I consider like sine of x, well, really sine of 1 over x is a better example, because we sort of already talked about this. Lim x goes to 0, sine of 1 over x. If you do this using a sequence, I can say something like choose xn going to 0. I mean xn equals 1 over pi n. This is one of the ideas that we discussed before. Then f of xn, if you recall, this equaled sine of pi n, which is the sequence 0, 0, 0, 0, which converges, right? So in this example, the sequence converges, but the original function does not. Remember, this is that function with the graph that I showed you, that weird, insane oscillation. So in this case, that sequence of points does converge, but that does not mean that the function limit exists, all right? So it's possible the sequence may converge even if the function limit does not exist. This is why it's not enough to use sequences to prove that the function's limit exists. All right, that's my little warning. Any thoughts about that? This I can remember. I think last year, maybe last year. Some people on the comprehensive exam messed this up. They tried to show that the limit of a function equals something by demonstrating sequences. It's not good enough, folks. Speaking of the comprehensive exam, you should get your official notification about it tomorrow. It's a little late this year because we forgot who was in charge of the comprehensive exam this year. I say we because it's me. I thought for some reason that it was Professor Rafalski, but it's not. It's me. So, but yeah, you will be hearing from me tomorrow about the comprehensive exam. All right, we got about 10 more minutes. I think that's enough to talk briefly about continuity, a continuous function, right? Let's talk about continuity of functions. This, of course, is a big deal in calculus and in analysis. Continuity of a function. A function is continuous. You know, in a calculus class, they say a bunch of mumbo jumbo about like lifting your pencil off of the paper. I'm not going to say anything like that. A function is continuous. It's actually not hard to say the definition, and you can use the same. If you look in a typical calculus book, they will say what I'm about to say. I'm going to say a function f of x is continuous. I'm going to talk first of all about continuous at a point. Let's say continuous at C when lim x goes to C of f of x. You remember this definition from calculus? F of C, yeah, great. It means kind of as your variable approaches a specific value, that function actually approaches that same value. It means you can, this sort of is like, you can just plug the value into your function and you get the right answer. That works for a continuous function. All right? This is the definition of a continuous function. Now, we say this in a calculus class to kind of obscure the fact that we don't really want to talk about exactly what this means, but we just say this like some kind of closer and closer sort of a thing. Now, if you want to write this out in full detail, so in detail what it means in terms of the epsilons and deltas, it means for all epsilon greater than 0, there exists delta greater than 0 such that I'm just going to write the limit equals f of c. So what that looks like is 0 less than x minus c less than delta implies f of x minus f of c less than epsilon. This is just the same as our usual epsilon and delta thing, only instead of the big L here is this number f of c. And so there's some kind of pleasant little symmetry to this, right? Here you have x minus c, and here you have the same thing but with f's wrapped around it. All right? Or there is one more version. So these are equivalent. Another version with sequences. You could say for all sequences xn approaching c, we have the sequence version of this would be if xn's are approaching c. Can anyone say what the conclusion would be? Yeah. Yes, I want to say in terms of the sequences, f of xn approaches f of c. Yeah, great. So these are sort of three different versions of the same thing, all right? For all sequences, if you want to do it in terms of sequences, it's here. All right. I think we got time for one example. Let's just try. This will be fun. Since we haven't done any epsilons today, we got to get that in there, right? Let's show f of x equals square root of x is continuous at x equals 4. I think we got enough time to do this. We have 6 minutes. Continuous at x equals 4. All right? Let's first of all rephrase this in terms of limits, because that's what this is about. So I'm just going to use the definition that I wrote up here. Continuous at c means this. So I'm going to rewrite this thing. This says continuous at x equals 4. So let's just write that. It said lim x goes to c, and playing the role of c in this case is 4. And then I put f of x here, which is root x, equals, what should I say on the other side? I heard some people said f of 4, which is right. F of c would be f of 4, which is the square root of 4, which is 2, right? So over here goes root 4, which is 2, all right? So I want to show, lim x goes to 4, root x equals 2. And from now on, it's just like one of those other problems that we've done a few times before, yesterday, right? This is just a standard showing the limit equals something. So let's try to do it. I will say let epsilon greater than 0 be given. In 5 minutes, I think we can do it. We'll find delta greater than 0 such that 0 less than x minus 4 less than delta implies root x minus 2 less than epsilon. I don't think we've done any examples with the square root function here. It requires another special trick. Like I said last time, each time you see a new kind of function, you have to do sometimes some random trick based just specially for that function. Last time we had some kind of weird factoring of a cubic. This time we have root x minus 2. Anybody remember any tricks you can do with that? There is one trick that I remember from calculus about the square roots, which sometimes does something. Yeah, you know all the tricks. Yes, this is the one where you multiply by what they call the conjugate. So I'm going to turn this into root x minus 2 times root x plus 2 over root x plus 2. Anyone remember that trick? This is another obscure trick. I wouldn't really expect you to do this on a test or anything like that. I'm not big on making you remember these obscure tricks, but on the homeworks, perhaps. All right. What's the point of doing this? I combine them together in the numerator, so this becomes root x minus 2 times root x plus 2 over root x plus 2, right? And then the multiplication in the numerator it turns into a difference of 2 squares. And what you get is the square root of x squared, which is x, minus 2 squared, which is 4. And now you see that the magic has happened, because I ended up with x minus 4, which is this thing that I wanted to end up with. All right? But I also have that other piece, so maybe I'll sort of separate this out just to keep straight. It's like that, right? And I like the x minus 4 the way it is. I do not really like the root x plus 2. Anyone want to suggest how we should handle the other part? Yeah.
The delta less than 0.
It's the old delta less than 1 trick that you did last time, and there's at least one on the homework where you want to do this. So I'm going to say let delta be less than 1. And that means, delta is how far away x is from 4. So if x is within 1 of 4, that means it's between 3 and 5, right? And basically what you do is you end up plugging one or the other of these numbers in for x here. Is it the 5 or the 3 that I should use? It's the 3. Because it's in the denominator, you want to make this thing as big as possible. Because it's in the denominator, I use the smaller value, because I'm dividing by a smaller value, which ends up being bigger than dividing by a bigger value. Anyway, I get x minus 4 times 1 over root 3 plus 2. And that's my weird constant, root 3, 1 over root 3 plus 2. But that, just to make the algebra simpler, root 3 plus 2 is something like 3.7 or something. Would you all agree that this is true? That's 1 over 3 point something or other. You can just throw that away and say that's less than or equal to x minus 4, so that I don't have to say something like, I'm going to use delta to be epsilon over 1 over root 3 plus 2. I'm not into that. All right? So, sorry, it's time to go. I say let delta be the min of 1 and just epsilon, because I ended up with nothing else here, right? This thing times 1. You know, I don't have to do epsilon over 2 or epsilon over 5 or whatever. It's just epsilon. Can I just say, because it's time to go,